the financial world, to make trading decisions, to make bail decisions in the justice systems in the US, to make medical decisions. Similarly, advances in automation, robotics are completely transforming retail and logistics, right? So, I know it's pretty clear to me that the impact of this technology is going to be really, really transformative. It might be the case that, as some scholars are claiming, that we're really at the beginning of a new industrial revolution. And so the key question that I spend a lot of time thinking about is, how do we actually make sure that we can use this technology, these amazing technologies that we've all been developing, to benefit as many people as possible? How can we make sure that these technologies are not going to be used to further increase inequalities, but they're actually going to be used to promote the well-being of humanity throughout the world? So in my research, I think a lot about issues of sustainable development. What you see here are the 17 SDGs that were identified by the United Nations as being some of the key priorities that the international community should be focusing on. And you see problems like ending extreme poverty, or fighting hunger, or finding new sources of affordable and clean energy, fighting climate change, reducing inequality. And so clearly, to the problem that if you don't have good data about these kind of problems, like ending poverty or ending hunger, then it's very, very hard to figure out how should you allocate resources, to which programs should you give the limited money that a government might have access to. How do you figure out if the policies that governments are implementing are actually working or not? Or if there are different social programs, which one should you fund? Right? Or even just figure out, are the social programs that you're implementing actually working or not? Right? So, just to give you an example, we know that the number one goal that we had on the list before is the problem of ending extreme poverty. The international poverty line is $1.9 per day. And that's a huge problem. There is close to 600 million people that still live in extreme poverty, many of them in this continent. And the reality is that we really need, if we want to solve this problem, if we really want to end extreme poverty by, let's say, 2030, what we really need is good data to figure out what kind of policies we need to implement, which policies are working, which ones aren't, figure out if we're making progress, right? It's very easy to set a target, end extreme poverty by 2030, but then whenever you set a target, the target needs to be measurable. You need to be able to figure out if you're making progress or not, and just try to get a better understanding of the problem, figure out which policies work, which ones don't, what are the kind of socioeconomic factors that can explain the variation that we see exists on the ground for these kind of outcomes. So the way governments and organizations typically collect data on poverty is by doing surveys, household surveys. Surveys are pretty expensive, and as a result, they are not done very frequently. Here I'm showing a map of the African continent, and every country is color-coded by the number of surveys that were done, that were conducted in that country in the decade from 2000 to 2010. And as you can see, many countries, well, the lighting is not great, but what this map shows is that for a lot of countries, we just don't have good data. Many countries did 0 surveys, maybe they did 1, maybe 2. The maximum that you see is 4. Right? So we're setting these targets like end extreme poverty, but then we don't have data to figure out if we are achieving these targets or not. Right? Even when you have data, the sampling is very sparse. It's expensive to go around and collect data door to door, and so you maybe sample a few hundred, a few thousand households, and it's not very, very accurate. It's not very both over time and over space. The detail that we get is just not as good as we would like it to be. Right? So how can we actually come up with a different way of estimating these kind of socioeconomic indicators that we would need in order to come up with better policies, better solutions, do better research. If you're in the social sciences and you want to do research on these kind of problems, you need access to better data. So is there a way in which we can actually collect data in a more inexpensive, more scalable, better way? So one of the sources of data that we've been looking a lot over the last few years is satellites. It turns out that there's been a lot of progress in remote sensing. The kind of data that you can get from space is getting better and better, cheaper and cheaper, and of higher and higher quality, right? So this is an image, I believe, of somewhere in Uganda from the Landsat sensor, which is kind of like the best you could have gotten about 10 years ago. You cannot see much because of the lighting, but even if you had better lighting, you wouldn't be able to see very much. Every pixel here corresponds to an area of 30 meters by 30 meters on the ground. And the detail in this so the resolution is basically so low that you can't really see much about what's really going on the ground. Nowadays, we get access to much better imagery. Again, I think, unfortunately, the lighting is not great, but we basically get access to images that have maybe 2-3 meter resolution. So every pixel corresponds to an area of, let's say, 2 meters by 2 meters. And there you can start to see a lot more about what's going on the ground. You can start seeing buildings. You can even get access to, if you're willing, these kind of images are basically available everywhere in the world, and they are updated very frequently, like every day. So the temporal resolution is really, really good. If you're willing to accept images that are updated less frequently, you can get even higher resolution, maybe 30 centimeters. Every pixel corresponds to an area of 30 centimeters by 30 centimeters. And here you can really start seeing a lot more about what's going on the ground. I don't know if you can see, but on the left, I put an image of a shipping yard. And you can see ships, you can see containers, you can see a lot of detail about what's going on the ground. You see here some houses. You can see the kind of roofs the houses have. You can see a mine here. You can get a sense of how deep it is, you can get a sense about the level of economic activity that's going on. You can see vehicles, you can see fields, you can see how the landscape is changing over time. These days, you can even get access to high-resolution videos from space. This is an example. This is something that is available commercially today. This is not something that just intelligence agencies have access to. It's something you can buy. High-resolution video of a power plant, I think somewhere in Maryland, where you can see the smoke coming out from the chimney. And again, the idea here is that there is a lot of information that is hidden in these images. You can get a sense, you can figure out a lot about what's going on the ground if you had access to a way to basically extract this kind of information automatically. And that's basically the idea. But maybe before I get into how we actually developed machine learning and computer vision techniques to extract this kind of information automatically, let me tell you a little bit more about the kind of remote sensing data that is available today, so that if you want to follow up on this kind of research, you want to estimate different kind of indicators, you can get a sense of the kind of data you might be able to play around with. A lot of the data is actually available for free. It's publicly available. Things like Landsat, MODIS, Sentinel. These sensors, these satellites, are typically built by space agencies, European or NASA. They have different kinds of resolution, maybe 30 meters, 500 meters, 10 meters. And they're updated with different kind of intervals, maybe 16 days, 8 days, 5 days. And the images that you get from space, they're not like the regular images that you play around in computer vision. It's not just RGB, but you often have access to other bands, like thermal bands, where you can get a sense about the temperature, infrared, near-infrared, radar sometimes. And if you're willing to buy products, you're willing to spend money, you can get access to much higher resolution imagery from Digital Globe, maybe 0.5 meter resolution, 30 centimeter resolution, something like that. Planet Lab That's the kind of data I showed you before. They are a startup from the Bay Area. They have their own satellites. They have like a constellation of hundreds of really, really small satellites. Their data, they are able to take an image basically of the whole world, updated every day at about 2-3 meter resolution. Right? So for every part of the world that you care about, you can see at that kind of resolution, and you can see how things are changing over time with sort of like 1 day intervals. So that's kind of like the temporal resolution. You can think of it as a video where you get a frame every day. One challenge that you might need to consider if you want to do sort of like large scale analysis of these images using computer vision or machine learning techniques is that you typically need to deal with a lot of data. The scale is pretty massive. That's the beauty of it, because you can really do large scale computations and large scale analysis. On the other hand, it kind of requires fairly large computational resources, but luckily you can do it on the cloud. I'll show you some examples of that later. But just as a back of the envelope calculation, let's say that you're dealing with Landsat. As we said before, the resolution is 30 meters. It means every pixel corresponds to an area of 30 meters by 30 meters. So that's 900 square meters. That's approximated to 1,000 square meters. Let's say that you use 2 bytes to represent every pixel, just as an approximation again. If you want to cover the entire continent of Africa, that's about 30 million square kilometers, which ends up being something like 30 times 10 to the 6 times 10 to the 6 square meters. Every pixel corresponds to 1,000 square meters, so that's about 10 to the 9 pixels. If it takes you, let's say, 2 bytes per pixel, that's about 60 gigabytes. If you want 3 bands, let's say RGB, that's about 200 gigabytes. If you want 1 image per month, that's about 2.5 terabytes. So they're pretty big data sets. Luckily, you can do everything on the cloud. The data is available for free on Google Earth Engine. So you can do all the processing, all the machine learning you want to do directly on the cloud. And then if you need, you can basically copy the data locally on your computer if you want to do training, if you want to do other kinds of experiments. So, and the code is simple. Like, I guess you don't need to read it, but sort of like the code that you need in Python to export all the images for a particular area over a certain period of time is actually pretty small, right? It's like, I don't know, let's say 10 lines of code, something like that. So there are nice Python libraries that you can use to pull the data, process it, and do all the machine learning that you want to do, right? So this is just to say that if you want to play with this kind of data, you want to apply it to a problem that you are passionate about, it's not too hard to get started. We actually have some tutorials, we have some notebooks that are available on our Sustain Lab group website at Stanford, and so you're welcome to play with them and use the starter code and do and apply these kind of ideas to other sort of problems. So the general idea of the kind of projects and research work that we've been doing is the following. So we have access to this remote sensing data, and we would like to apply AI and machine learning techniques to come up with insights that we can use to improve policies, to track accountability, to do social science research, all the things that we saw before that are sort of like impaired by the fact that we don't have good data about what's going on the ground. Whether you care about health outcomes, whether you care about poverty, whether you care about food security, better data would allow us to come up with better solutions to these problems. And the idea is that if we use satellite images as an input, we get a lot of advantages because they are high resolution. As we saw before, there is a lot of information contained in the images. They are collected regularly. They are updated frequently. And they are constantly improving. They are available everywhere. They are constantly improving. And so the idea is that there is hope for sort of like using these new sources of data that are cheap, globally available, scalable, combine them with the latest advances in AI and machine learning, and use them to, let's say, come up with a detailed poverty map or a map of economic well-being for, let's say, the whole African continent that we can keep, that is very high resolution, goes down to, let's say, the village level, and it's updated, something that we can keep updated very inexpensively, because the only thing that you need is to get new data, just feed it into your machine learning model, and you get a new map. And it's sort of like much more inexpensive than traditional surveys, which, as we've seen, are not done very often. They are not done very frequently because they are just too expensive. And so the kind of like the technical challenge, the reason why maybe this has not been done before, or why this is not entirely trivial, is that although we have a lot of images, they are unstructured, so there is sort of like a challenging computer vision problem in going from the images or the videos to the kind of insights that we care about. And the other challenge is that there is not a whole lot of training data. I think that's something that came up over and over in the talks that I've seen here at this meeting. The fact that we want to build these maps is precisely because there is not a lot of good data on the ground about these kind of socioeconomic indicators that we care about. And so a lot of sort of like the research goes into figuring out clever ways for providing supervision to these machine learning algorithms in different ways that are sort of like, they don't require us to collect an ImageNet-sized training data set in order to get good performance and come up with accurate estimates for these kind of indicators that we care about in a more scalable and inexpensive way. So that's kind of like, it's going to be the main topic of this talk. It's going to be about some of the techniques that we've developed to get around the labeled data scarcity and be able to come up with these very high resolution, very large scale maps of different things like economic well-being, access to infrastructure, crop yields. We'll see several examples of the kind of things you can estimate from space by sort of like getting around the fact that often for these problems, we don't have a whole lot of training data available. Sort of like you cannot just take your favorite deep learning model and just train it end to end because there is not a whole lot of training data available. So before we go into this, are there any questions? Feel free to interrupt at any point if you have any questions on the main idea or anything. All right. So let's go on. Let's talk a little bit about, oops, that's not smart. Talk a little bit about the roadmap. We're first going to talk about some transfer learning ideas that we've used successfully to get around the labeled data scarcity. Then we'll talk a bit about semi-supervised learning, and then we'll talk about unsupervised learning as a way to sort of like learn good features, good representations in an unsupervised way so that we can take advantage of the fact that we have a lot of satellite images and even though we don't have a whole lot of labels, we can still do pretty well at this task that we care about. So let's start with transfer learning, right? So the idea of transfer learning is that although we don't have a whole lot of training data to train a model that, let's say, predicts economic well-being, perhaps we can come up with a different task that is related, but it's much easier to solve, right? So the analogy here is that, let's say you want to learn how to fly a plane. You don't start with the real plane. What you do first is you spend hundreds of hours in a flight simulator, and you figure out how that works first, and then maybe you're able to see and play around with the real thing, right? As another example, let's say you want to learn how to play golf. Maybe the right thing to do is to start with a driving range where you can hit a lot of balls and you can improve your game before you actually move on to the real thing, right? So the kind of idea is that there is a target task that we care about, but it's hard because we don't have a whole lot of training data. And so what we're going to do is we're going to start with something that's easy. And easy here means that there is a lot of training data available, like the flight simulator or the driving range in the case of golf. So what's a good task, source task, for which there is a lot of training data available if the target task is to, let's say, predict economic well-being? Well, it turns out that nighttime lights are a pretty good proxy for economic development. Turns out that we have satellites that take images of the Earth, not only during day, but also during night. And the amount of nighttime light intensity that you see from space can tell you a lot about how economically developed an area is. What you see here is an image of the Earth in somewhere in Asia. Can anybody guess, if you can see it, where this is? Indonesia? No? This is actually China. This is South Korea. And this dark area in the middle is actually North Korea. Right? So it's huge, right? You can see clearly that the level of economic development is reflected by how dark or bright that area looks from space, right? It's completely dark. It almost looks like South Korea is an island, but it's not. It's just because there's not a whole lot of electrification and electricity in North Korea. Right? So the idea is that we can set up this source task, this transfer learning task, of trying to predict, let's say, try to train a machine learning system to take images of an area taken during day and try to predict how dark or bright that area is during night. Right? So if I show you these two pictures, which one do you think is brighter at night? Right? It's clearly the left. Like you can see buildings, you can see cars on the left, on the right, maybe it feels like it's kind of a barren areas, dirt roads. Clearly, there's a lot more human infrastructure on the left. And so the idea is that if we train a machine learning system to try to predict the amount of nighttime light intensity from the daytime images, the model will sort of like be forced to look for these kind of features, like are there cars there, are there buildings, are there big roads, that are also hopefully then going to be predictive for other things that we might want to predict, like economic development, like access to infrastructure, things like that. So what we can do is we can just generate basically a very large training set where we take as input a daytime image, and as output, as a label, we basically look at the amount of nighttime light intensity that you see for that location. And because we have images of essentially taken both during day and during night for the whole world, you can generate a training set as large as you want. Like you can just sample locations anywhere you want. You take the corresponding daytime image, the corresponding nighttime image, you put them together, and you have your training point, right? And then what you do is we have this source of question.
So why would you class that as a classification problem rather than regression?
Okay. So the question is why classification instead of regression? Regression also works. It turns out that classification works a little bit better. It's one of those things of neural networks. They tend to do better at classification than regression. And at least in our experiments, we found better performance doing classification. But it sort of works even if you do regression. So that's kind of like the idea. We have this source task where we're taking as input daytime images, and as output, we try to predict whether that location is dark, medium, or bright during night. And as a source task, as a target task, let's say we want to estimate economic well-being or poverty. And in this case, we take as input an image of a particular location that we care about, and we try to predict, let's say, some kind of measure of economic well-being. Maybe it's an asset-based measure of wealth that kind of captures the kind of things people own in that location. Or maybe it's a consumption-based measure of wealth, which is kind of like how much money people spend on various things in that on average, let's say, in that location. And the key thing to notice here is that we have a lot of training data for the source task. And so there is hope to then, by learning how to solve the source task, we might learn something useful that then we can transfer to the task we actually care about, which is, let's say, the one of regressing economic well-being. So the setup is the one that you've probably seen if you've done computer vision. You basically pre-train on this source task. Let's say you train a convolutional neural network to map images to nighttime light intensity. And then the hope is that somehow the features that this network will extract are semantically meaningful. They are also going to be useful for other kinds of tasks that we might care about. And indeed, it turns out that it does if you kind of like try to visualize the filters that the model learns in order to solve this task. They are meaningful. So here you see an input image on the left. You look at the activation maps of one of the filters. You see that they kind of like activate on the pixels that correspond to a road. If you look at another one, there is a water body there on the left. You look at the activation map of a different filter, and you see that it kind of corresponds to the water body. And there are many more. There is a filter. If you train this convolutional neural network, turns out that there is a filter that looks for houses, one that looks for tall buildings with a shadow, one that looks for traffic roads. My favorite one is the swimming pool filter. The model learns that looking for swimming pools is useful for predicting nighttime light intensity. And again, what's interesting here is that we didn't have to provide any labels. We didn't tell the model, oh, this is a swimming pool. We didn't provide any bounding box, any labels. We just pre-trained on that nighttime light prediction task, and automatically we got a pretty decent feature extractor. And now that we have this feature extractor, we can hopefully use these features to, let's say, regress on some measure of economic well-being that we would like to estimate at scale. And so that's kind of like the idea. We have a few locations for which we have survey data available. This is typically survey data collected by governments or the World Bank. For every location, we take the corresponding satellite image, we feed it through this pre-trained model, and we extract a lot of visual features of that particular location. We do this for every location for which we have survey data available. We look at some variable, some measure, some quantity that is measured in the survey that we care about. And then we train a simple model, say some kind of ridge regression model that will try to predict the survey variable we care about. This could be consumption, or it could be some kind of asset-based measure of wealth. And we try to predict it directly using these rich visual features that we've been able to extract using this pre-training strategy. And it turns out that it does pretty well. Here you see an example of how the model does in Uganda when we try to predict the data that was collected in 2011. So every dot here corresponds to a location that was surveyed in this DHS survey. On the x-axis, there is this is an asset-based measure of wealth. It's kind of like a PCA representation of the kind of questions that were asked the people on asset ownership. Things like, how big is your house? Do you own a refrigerator? Do you own a radio? There's a lot of questions in the survey, and then people compute some kind of PCA loading, and then they come up with an asset-based measure of wealth, which is often used in the development economics literature. Every dot here corresponds to a village or a location for which we have survey data available. On the y-axis, so on the x-axis, there is the true value measured by the survey. This is the expensive way to collect the data, the traditional one, household surveys. On the y-axis is the estimate that we get just by looking at images of that location and the model that I just talked about. So ideally, you would want to be on this diagonal line, meaning that the predictions are identical to the ground truth. And you see the model is not perfect, but it's getting an R-square of about 0.7, which means that we can explain about 70% of the variation that we know exists on the ground just by looking at satellite images, right? And so this is, although it's not perfect, it's kind of like understandable. There are just some things that you cannot see from space, but this was really, really encouraging. This is much better than anything that was available before we came up with this solution. And so What this means is that now we can fill in the gaps. Yeah, question?
So how does the performance compare with, say, just doing end-to-end on the image?
Yeah, so end-to-end, it depends on how much training data you have. The numbers are in the paper. Typically, the performance is not good. Even if you do pre-training on ImageNet, which was kind of like the first thing we tried, it just doesn't work well because the images are so different. And then you also have extra bands that are sort of like not beyond the visible light that are very difficult to initialize when you use a pre-trained ImageNet model. And so I think the numbers are in the paper, but it was not nearly as good as what you can get with this kind of approach. Yeah? This one is a digital globe. Can you say it again? Yeah, good question. So the question is, you know, where are we making mistakes? And I think we don't know exactly. I think there are several possible explanations. We know that the ground truth measurements themselves are not perfect. There is a lot of measurement noise. We know there are things we cannot see from space. We cannot see inside people's houses. So there's certainly a bunch of stuff that we just cannot possibly estimate from space. And then probably we just didn't do a good enough job at training the model. I'm sure you can, if you work hard enough on it, you can probably improve the performance a little bit. But I would imagine that there is a little bit of a ceiling. In fact, we've done some exercises where we tried to, in some countries, there were like kind of two sources of data available, and we tried to see to what extent they match with each other. And the errors were sort of like comparable to the ones we get from our estimates from space, which means that there was a lot of measurement noise just in this original survey data that we used. Yeah.
How do you address accuracy of math data? Sometimes satellite data, the level data is more activity, tends to be like satellite data very less accurate.
That I'm not, I mean, there are issues with cloud cover. So the question is, how do you deal with the fact that sometimes the satellite images themselves are of low quality? So there's a lot of pre-processing that you typically have to do. One issue is cloud cover. There are some regions of the world that are often covered by clouds. When there are clouds, you cannot actually see what's beyond. And so there is some pre-processing that goes into trying to come up with clean images. It's fairly standard stuff. It's kind of like compositing the images to get a clean one. Beyond that, we didn't do much, we didn't do anything special except just training the model, and to some extent, hopefully the neural network also figured out how to deal with that. But yeah, we didn't do anything else specifically except the standard tricks of compositing and trying to do some cloud cover detection, the usual stuff, basically. Yeah? Uh-huh. Yeah, so that was cherry-picked. So, I mean, we found some that were interpretable, but indeed, yeah, you're right. There were hundreds of activations, hundreds of hidden units, and we explored a few of them. The students actually did the work, and they found some that actually that were meaningful. But there is probably a lot more that we don't know how to interpret. So I'm not claiming the model is interpretable. It's actually not. We don't know exactly why it makes these predictions. That's the kind of a usual problem that we have deep learning. We try to get a sense by exploring the filters, but we still don't know exactly how the model works. Yeah, manually. Yeah. Yeah.
Have you made any attempts to like model in a global context? So like if something looks the same but is nearer to the massive, economic hub, or south of the world.
Yeah, so I'll come to, when we talk about semi-supervised learning, we incorporated a Gaussian process regression model and a spatial kernel. So I'll come to modeling spatial temporal structure later. Yeah. We're doing regression. So we just take basically we take the pre-trained network, then we use the last layer features, and we just do a bridge regression on those. So it's just a scalar. That's what the network outputs. It's just a scalar. We're just doing regression. Where there is no softmax, at the end we just do regression. So it's just a scalar. All right, so now the good thing is that once we have this model, we can basically start filling in the gaps, right? So what we can do is now we can take locations that are shown in blue here that are unlabeled, meaning that we have images for that location because we have images for all over the world. And what we can do is, let's say there is a village, we would like to know the level of economic well-being there. What we can do is we can take the corresponding satellite image, we can feed it through our neural network plus ridge regression model, and we can get a predicted value. We can start filling in the gaps and figure out what's going on in the locations that were not part of a survey, let's say within a particular country. The other thing you can try to do is you can try to be even more ambitious, and you can try to train a model in some countries, and you can try to then evaluate the model. You can test it out of country. Like you can try to come up with maps for countries, let's say Somalia, for which no training data available, for which there was no training data available. And so you can, if you believe that the model will generalize, that a model trained on a bunch of African countries will then work well in Somalia, then you can try to fill in the gaps even more by basically coming up with this kind of large-scale maps for countries for which no training data was available at all. Yeah? Yeah, so with this different part of the countries, I guess that's something that we've seen in the previous scatter plot that was cross-validated. So the kind of R-squared that we showed before, like let's say 0.7, that's basically already accounting for the fact that you're testing the model in a part of the country where you didn't necessarily have training data. You can do the same procedure out of country. You can try to pretend you don't have data for a country, even though you have. You train on everything else you have, then you test on the country, and you can try to get a sense of how well it does. You can find, there is a table in the paper where we basically show how well a model trained on one country generalizes to a different country. And as you would expect, it turns out that if two countries are close to each other, the model works better. If you try to train a model in East Africa and then you test it in West Africa, it's not going to work very well. But if you train on all the African countries you have and you test on a new one, it seems to work reasonably well. Although less well than if you had training data for that country. So this is what we did actually at Atlas AI. So the kind of results I showed you before were done at Stanford as sort of like as part of a research project where we were trying to see to what extent it's possible, if it's even possible to do this at all, estimate economic well-being from space. After publishing the paper, we got a lot of interest from organizations that wanted to use the data. So with the help of the Rockefeller Foundation, we started a company called Atlas AI, where we've taken this research and we've scaled it up. So we've actually implemented this idea of coming up with a continent-wide map of, let's say, economic well-being that spans multiple years. And you can see here at the continent level, but we have estimates for every country for basically for multiple years because the images are available everywhere and they are updated relatively frequently. So if you want to zoom in, let's say in Kenya, you can see a map where you zoom in at the district level and you can see kind of like the variation. Here colors corresponds to, I think, is this consumption? No, this is asset. So this is an asset-based measure of wealth that is aggregated basically at the district level. But you can zoom in all the way to the village level, and you can see here blue corresponds to basically a low percentile in terms of like the kind of asset ownership, and red corresponds to a high percentile of asset ownership, so it's normalized within country. But basically red here corresponds to a richer area, blue would correspond to a poorer area. And we're able to come up with a map with extremely high spatial resolution and reasonably good temporal resolution for the whole African continent, where you can see village by village, basically, how they compare to other villages in the country. And you can see how, by looking at changes over time, you can get a sense of how the situation is changing on the ground. I don't know if I have a map of that. No, maybe I don't have it. But there is a website. You can play around with it. You can zoom in. You can see whether we're doing a good job in, I don't know, an area where we're from, or a country where you have a sense of what is the real situation on the ground. And we're happy to get your feedback. If the model is making mistakes somewhere and you know about it, please let us know, and we'll try to fix it. But the kind of evaluations that we've done, where we try to train a model in a subset of countries and test it on a different one, we're reasonably confident that the estimates sort of like make sense. Yeah.
What kind of methods do you try to use to show external biology in your regression sensitive to country?
Could you say it again?
What methods in your regression have you used for showing external validity for the regression model in your country?
It's basically just leave one out, cross-validation. So we try to train on a subset of the countries and then test on one where we pretend we don't have. It's just like cross-validation, but we group the data by country, and then we test on a separate country that has not been seen during training.
But how do you show that this data there is external validity because countries' situations are so different?
Yeah, so that's the best we could do, let's say, because that's the closest we can get to the situation where we actually produce data for a new country. We have no idea whether the map for that country is any good, because there is no ground truth data to validate it. Maybe old data, that's something that we did, but the kind of like the best we can do to get a sense of how well the model does is do this kind of like cross-validation kind of thing, where you train on a subset of the data, you withheld some of the labels, and then you try to see how well you did. And that's kind of like the best metric we have. Yeah. Leave one country out. Yeah, that's what we did. Yeah. Yeah. So. Yeah, so the value is that it's much better. So the question is, why not just use nightlights? And the reason is that nightlights doesn't perform really well. There are many areas that are completely dark at night, but still have a lot of variation in economic well-being. And if you just use nightlights to make predictions, then you're not going to capture any of that variation. But there is differences in the daytime images, and the model is able to actually capture some of that. So the advantage is that the predictions are more accurate, but less interpretable. Yeah?
What's the resolution of the predictions? In a village, can you see concept of village low and up?
Good question. So the question is whether we can, what's the resolution, and if we can, within a village, let's say, capture any of the within village variation. And the answer is we cannot capture any of that. Basically, we are, the best resolution we can get is the one, we are basically bounded by the quality of the training data that we have, which is aggregated at the level of an enumeration area. And so that's basically the best we can hope to get. I think in principle, the images are detailed enough that you might be able to capture some of the variation. But we don't have any training data to train a model or to evaluate whether the predictions that we make any sense, because there is no ground truth to actually evaluate how well we do. So we always aggregate at that level of the enumeration area. Yeah? How many? Yeah, it depends country by country. You can see, like for Uganda, this is what we had. So it's not, it's probably, it's a few hundred data points, so not very many. In total, good question. Some countries have many more, like Nigeria has a lot more. Some smaller countries have less. So, I mean, it's in the order of thousands of data points, something like that. Yeah?
I just want to ask around reaching this work, things like DPI, data poverty index, plus the telecoms data for poverty that have been done by
So,
data,
yeah.
feature engineering is going to need to
So
work.
telecom data is another source of that people have explored before to try to make these kind of predictions. Basically CDRs, called data records, and we've compared to their accuracy. It turns out that we can do, let's say, there was a science paper where people try to predict poverty using CDRs. It turns out that we can do better than them, and we don't need. That's kind of like privacy-sensitive data that's very difficult to get your hands on. And so we were really happy that we can get better performance using a much more widely available data. But I think there is probably added value that we could, if we had both, you could probably improve even more. Yeah. So we basically train the model once over all the years. And then, so that's basically what we do. But you're right that in principle, let's say, there is a shift. There is definitely a covariance shift that we should probably take into account. I think that's a good point that we might need to retrain the model occasionally as it's kind of like the landscape changes over time. Yeah.
Have you experimented with OpenStreetMap data? Like there was recent work by Facebook on high resolution density maps using that.
Yeah, so we've experimented with it. In fact, I'm going to talk a little bit about some other sources of supervision that you can use to kind of like pre-train the model. We've used nighttime lights, but you could also use OSM, OpenStreetMaps. We've used Wikipedia. I'm going to show you soon another. In fact, I think it's in a few slides. I'll talk about other sources of supervision. Anyways, we did this work. Of course, the first thing that we did after coming up with these maps is we made a video. We put it on YouTube, and of course, people were really excited about our work. And wondering why you don't know the corresponding label. You have the X's, right? You have a lot of inputs. You don't have the outputs, but you have a lot of inputs. And so this is kind of like the perfect setup for semi-supervised learning methods, where you have a lot of data that is unlabeled and a small fraction of data points that are actually labeled, in this case locations that are shown in red, for which we have a ground truth measurement through a survey. So how can we leverage the fact that we have a small amount of data for which we have X and Y, and a large amount of data for which we basically just have the X's. We don't have the corresponding labels. So the basic idea is to take advantage of some of the tools that people have developed in semi-supervised learning. And the typical kind of like intuition behind semi-supervised learning is the following. Let's say that you're trying to, let's start first with classification, then we'll move into regression, but let's start with classification just to get some intuition. Let's say that you want to learn a classifier that distinguishes between blue and red class. And let's say you only have 6 training points, so you come up with this kind of classifier. And let's say it's a linear one, it's kind of like a simple linear decision boundary. Right, so if you just have this labeled data, this is perfectly reasonable. It's a pretty good decision boundary. You have no reasons to believe that this is not good. Now let's say that now I add a lot of unlabeled data. These are shown as gray dots. Now would you still, so this is, now I add the unlabeled data. Would you still think this is a good classifier? Or would you want to change it? Right, so maybe you want to shift the decision boundary that way, right? And the intuition is that you basically, even though you don't know whether these points are red or blue, you want to make sure that you choose a decision boundary such that the predictions that you make at unlabeled data points, that you're going to be confident on the predictions that you make. You want to reduce basically the uncertainty that you have on the predictions that you make on the unlabeled data points. And that's kind of like the basic idea behind almost all existing semi-supervised learning methods. And so the idea is that we would like to apply this to semi-supervised regression, right? And the first question is, how do we actually quantify uncertainty in regression? So let's say that we have our neural network, takes as input an image, and produces, let's say, an estimate of per capita consumption in that location. Now, somehow, if we want to leverage this kind of semi-supervised learning techniques based on minimizing the uncertainty, we need to have a sense of how confident we are in the predictions that we make. It's not sufficient to just come up with a number, which is what you would normally get with a regression model, map an image to one scalar, a number. You also need to know how confident you are in the predictions. Maybe you want to know that you are not so confident about this one, you have a plus or minus $3 kind of error, but you are more confident about this particular location, right? And so, in order to do semi-supervised learning and kind of like be able to say, oh, I want to minimize the uncertainty on the unlabeled data points, we need to have a model that is able to quantify its uncertainty. So in order to do that, we need to have access to a distribution over functions, not just a function that maps inputs to outputs, but we need a distribution over functions. So here we're going to use a Bayesian approach. So what we're going to do is we're going to start with a prior distribution over what are reasonable mappings from inputs to outputs. So just as an example, we're going to use per capita consumption, say dollars per day as an output on the y-axis. And let's say that we try to predict it as a function of latitude, just a single variable so that I can just plot it as a one-dimensional plot. So what do we know about the relationship between, let's say, latitude and per capita consumption? Well, maybe we know something like the average level, the average per capita consumption. We know a mean value. And maybe we know that the relationship between inputs and outputs should be smooth. So if you change the latitude a little bit, then the output shouldn't change by too much. And the fact is, if this is all you know about the function mapping inputs to outputs, then there are many such functions that are consistent with this prior. Here is one, here is another, here is another. So there's a whole distribution of functions that are consistent with the prior that we have. Now let's say that now we have some training data. I tell you the value at this particular latitude. I know for sure I actually sent somebody on the ground and take a measurement, and I know that the value is this. Then we should update our prior, and we should get a posterior distribution, because now we know that the function has to be consistent with this observation. And so now we update our belief about what are the possible mappings between inputs and outputs, and now we get a family of functions that might look like this. Now let's say that we add another measurement. Now we should update again our belief about what is the actual mapping from inputs to outputs. And so maybe we come up with a new family of functions. Then let's say we have another training data point, another measurement, we come up with a different distribution of our functions. So what you see here in this animation is that getting observations basically reduces our uncertainty about what are the possible mappings between inputs to outputs. Right now we know something about what happens at these locations and close to those locations. In particular, we have low uncertainty near the observations, because there are less functions that are basically consistent with these measurements, because we know that the relationship has to be smooth. And when you're far away from an observation, from a measurement, then the uncertainty is much higher. There are many, many functions that pass through these points that are locally smooth. So how do we represent a distribution over functions? Well, we can think of a distribution over function as a collection of random variables. Basically, there is a random variable for every possible input. So we can think of it as a stochastic process where there is a random variable for every possible input, which is basically the corresponding output, f of x1 through f of, and there is an infinite number of those random variables. So we have a collection of random variables, and what we're going to use is a Gaussian process to model this collection of random variables. if you think of it, any finite number of these random variables is just a random vector. And the assumption is that this random vector is distributed as a Gaussian random variable with some mean and some covariance. This is the basic, this is a crash course on Gaussian processes if you haven't seen them before. So where do these mean and covariance come from? Well, the idea is that there is going to be a mean function that will map inputs to the mean value at that corresponding, let's say, location, at that place. Then there is a covariance, which basically captures how similar two inputs are according to what you know about the relationship between inputs and outputs. So before any observation, maybe you have a prior mean, and you have some, after some observation, it turns out that you update the posterior belief, and it turns out that because of nice properties of Gaussian processes, the posterior is itself a Gaussian process with a different mean. And basically, the covariance function, which is the thing you need to describe the covariance of these random variables, can take many forms. For example, it could be some squared exponential, which says that if 2 points are close to each other, then they are more likely to have similar values in this kind of output that you're trying to model. And now let me go a little bit quick here, but basically the idea, the intuition, the key point here is that because of this choice, where you're saying if 2 points are close to each other, then the covariance is high. Then what happens is that you're basically saying if I have a new location for where I don't have a measurement, I'm going to have low variance for that random variable because I know that it's close to a location for which I have an actual measurement. So the problem is that in our actual setting, the inputs are not just one-dimensional variable, let's say latitude, but we're trying to do regression over images. And so let me go quickly here, but basically the problem is that you cannot compare images in pixel space. We've seen that before. And so the solution is to basically, in low dimensions, you can just build a Gaussian process based on the inputs. For high-dimensional images, what you want to do is you want to build a Gaussian process on the features extracted by a convolutional neural network. Right? So it's just like before, except that now you're building the Gaussian process on a set of features that are extracted by the neural network because you want to be able to compare points in a space that is sort of like lower dimensional and more semantically meaningful, where it's easier to compare different data points. So going a bit quick here, but the idea is that you can still train these systems end-to-end, these models end-to-end. You can basically train both the neural network and the Gaussian process to fit the data. And the idea is that now we're able to incorporate unlabeled data. We can actually do semi-supervised learning. So let's say that we have a neural network that gives us this kind of fit to the training data that we have. Then we have another, here the dots corresponds to observations. Then we have some kind of posterior variance that is given by the Gaussian process. And now I give another neural network that will give us different features over which we build the Gaussian process, and that will give us some other fit to the training data. Let's say that these two neural networks fit the data equally well, but you have no reasons to pick this neural network over this neural network. But now, just like before, if you have now unlabeled data, shown as orange dots, now which model would you prefer? The second one, right? The reason is that basically what happens is that the second model is more confident in the prediction that it makes on the unlabeled data points. The unlabeled data points are closer to the labeled ones, and so the prediction that the model makes are more confident. You see the variance at these locations, at these data points, is smaller than here. And so the predictive variance on unlabeled data points is higher on the left model than the right one. And so intuitively, just following the kind of like idea that we had before about the classifier, we should prefer model B over model A. And so it turns out you can write down a learning objective to do this. where you basically do something semi-supervised. You try to fit the labeled data as well as you can by training both the neural network and the Gaussian process hyperparameters. And at the same time, you try to make sure that the representations that you learn for these unlabeled data points are such that the unlabeled data points end up being closer to the labeled ones, even though you don't know what is the ground truth value for these unlabeled data points. You try to choose a neural network such that they get mapped to a location that is closer to the ones where you have training data. You're kind of like looking for features such that the unlabeled data points end up being closer, they end up being more similar to the labeled data. And it turns out that if you optimize this objective, it gives you some improvements. In particular, what you can do is you can incorporate spatial correlations. This was suggested before. What you can do is you can choose a kernel where you just look at similarity over the image space, but also similarity in, let's say, latitude and longitude, so geographically. And if you combine the two kernels, you're going to get a significant improvement in the kind of accuracy that you get by, let's say, in the poverty prediction task. You can basically significantly reduce the root mean squared error by basically taking advantage of the fact that we have a lot of unlabeled data. So this is a general strategy that we had this paper at NeurIPS last year, basically showing how you can do semi-supervised regression by combining Gaussian processes and neural networks and using this kind of idea of reducing the uncertainty on the unlabeled data. Works generally on a number of different data sets, including this poverty prediction problem.